Hey everybody, my name is Anil Kulkaram. I am the head of Department of Electronic and Electrical Engineering here at Trinity College, and my program co-coordinator, Professor Biswajit Basu, is also responsible for the design of this program in computational engineering. And I'd like to speak today a little bit about what this program entails and what is it good for. You could find more information on this website here. Okay, you've seen this story before, right? Technology continues to evolve and affect lives, careers, jobs. You hold in your hand a mobile phone that contains the collective knowledge of the entire world at your fingertips. It's a lovely collaboration between hardware and software that brings you both entertainment and information. And you've seen all these sorts of devices before, entertainment is full of information processing, hardware and software. Your home assistant combines both sensors to listen and speakers to speak, and they sort of embody the most advanced technology that you might have at home right now. And the car continues to evolve with increasingly more information processing engines. So the thing is that with the evolution of these products, it is now no longer enough that you know how to write software or you know how to design hardware. To be an effective contributor in a product development and design team, you need to really join deeper knowledge of signals and information processing together with these application level skills, writing software, designing hardware, and so on. And this is what we call computational engineering. So we are building the design engineers of the future who could distill information appliances down to their bare essentials and modify or create new technology from these core principles of computational engineering. And okay, I guess the subtext here is all of these things together help you survive as an engineer in this new age of automation. And I've been using this headline from The Economist since 2017 to encourage my students to think about the impact of automation on their lives. Now, the other thing you might want to find out about is, what are the jobs that you could go on to if you study computational engineering. And this is just a small cross-section from DSP engineer. Quantitative analyst is a pretty big one in the financial sector. Speech recognition designer, video coding, R&D engineer. But not only this, in computational engineering, your skill set covers a lot of scientific boundaries as well. So computational biology, and geophysical engineering, computational transportation engineering related to civil engineering, and so on. So in this program, there are a number of core modules in machine learning and computational methods that all students take, and then you can specialize in these different areas, right? And I will talk a little bit more about that shortly. So the program is a one-year MSc program, but there are staged awards. So you could opt to do 30 credits for a postgraduate certificate. Then you could upgrade that with 60 credits postgraduate diploma, and then into the 90 credits one-year master's. The program is offered from the electronics engineering department, and here is a cross-section of the people involved. Recently, we have started to restructure the department, so we spread across the breadth of signal processing, music and media technology, communications, and electronic platforms. The module choices for next year look something like this, and the ones I need to call out to you as part of computational engineering are these compulsory modules on deep learning and computational methods, and all computational engineering students must take at least 15 credits from these modules: geophysical simulation, quantum computing, cyber physical engineering, computational transportation, and digital signal processing. The computational methods module itself embodies the core practice of this course. So in this module, you work across 2 semesters. In the first semester, you work individually building your computational software engineering skills and skills in numerical methods. And this is really good actually for upskilling graduates from physics, mathematics, civil and mechanical engineering. And then in semester 2, students work in teams to complete a larger project involving motion picture effects. So another important aspect of this module that will change next year is exactly that project. At the minute, it involves motion picture effects, but next year it will involve a cross-section of different projects that embody the skill set in the class or the background of the class. So geophysical engineering, seismic engineering, as well as transportation and so on. Now, an important aspect of that module is this training in software engineering skills as they apply to computational methods and computational engineering. And so to facilitate that, we have a number of engineers coming in from industry talking from their own experience about the importance of this joined up skill set. So this year we had an Intel applications engineer talking about efficient deep networks, or building efficient deep nets, and how you could tailor convolution to be as efficient as possible in the early layers of a deep network. An NVIDIA engineer from Singapore spoke about the metaverse and the technology enabling the metaverse. We had a Huawei senior R&D engineer talking about computational software development in the sense of how teams must work together to exploit computational technology in the creation of products like video streaming engines or even real-time surveillance platforms. I can't stress enough how all of these speakers are concrete evidence that this joined up skill set between software and numerical techniques and underlying fundamentals of automation come together to create a valuable graduate that is in much demand right now. So a couple of the interesting modules that students find very popular. In fact, this one is compulsory. This one on deep learning, taught by Francois Pitié. Please go to his website, have a look at those lectures. He has them all up on his website, and he's done a fantastic job blending the latest in industry trends in deep learning with a kind of quick overview of the nature of machine learning itself. And you could find out more from his GitHub site there. The other modules in computational engineering span quantum algorithms, cyber physical systems and control, transportation simulation, and geophysical computation. And they're all quite popular, quantum and cyber physical in particular, especially because they kind of represent systems engineering concepts, and they are sort of approachable from students across a lot of different disciplines. I'll say a few words about the motion picture engineering module. I teach that. It turns out I won an Oscar back in 2007, so I'm able to draw on quite a wide range of experience to deliver this module, and students sort of get a mashup of motion picture special effects and streaming media technologies. A big aspect of the course is that you actually use industry standard software to develop novel novel video algorithms for motion picture effects. So here's just a quick example of a tracking tool that you work on as part of that program, that module. Also, as part of that module, we have some pretty influential guest speakers from significant engineering groups around the world. So this year we had talks from Simon Robinson, who is an Oscar winner, Dan Ring, the R&D director of a major manufacturer of software in the motion picture industry, Foundry.com, Professor Al Bovic, who is a two-time Emmy winner and professor at Stanford. He invented an important image quality metric. Next week, the students are going to hear from the YouTube video algorithms team in California about what it takes to launch products in YouTube. And then in 2 weeks' time, Yanis Katsavounidis is going to speak about video engineering at Meta. And previously, we had talks from people in Google Research as part of that Pixel 5 video algorithms team, and